Okay, this is our first lecture on special relativity. So today we're looking at special relativity. You remember before we said for classical mechanics, infinite number of coordinate systems. We had a Galilean transformation, and these were the different, this is how we described the two transformations between Frank and Mary. And then for electromagnetism, we said there was only one good coordinate system, right here. But we just showed, due to Michelson-Morley experiment, that this one good coordinate system could not be found right here. We could not detect this ether frame right here. And so Einstein, who was a patent clerk in Bern, Switzerland, matter of fact, I've been to his apartment in Bern, right here. It's just a little alleyway off the main street right there. But you can go up, they have a little museum of where he did all of his work in 1905. But he put a postulate out. And remember, he didn't even know about this right here. His postulate was, he said, why is there are an infinite number of coordinate systems for mechanics, but only one good one for electromagnetism? He said all the laws of physics, not just, these were the only two laws they knew about it then, those laws of physics right here are all the laws of physics are invariant. So that means that something's got to be wrong right here. First of all, if this is true, if all the laws of physics are invariant, that is, Frank and Mary agree on all the laws of physics, then we're back to impossible to detect. Impossible to detect absolute motion, to detect absolute motion, which made a lot more sense to him right here. Okay, so that means something is wrong because that doesn't fit with these two right here. So something has to be changed right here. Now, what are our options? Well, we could change electromagnetism so that it fits with the Galilean transformation, or we could change the Galilean transformation in classical mechanics so that it fits with electromagnetism right here. Now, by 1905, this had already been known. Maxwell's equations were only out about 50 years, whereas Newton's laws were almost 300 years at that time. But it took Einstein's genius to figure out that this is the one that made sense to him, and that one doesn't right here, which means he's saying that this is good, and that one isn't right there. Now, if you're going to say that this is the good one, and that's the poor one, and you're going to say that this is good for all coordinate systems, that means he had to add a second postulate right here. And since you have a C in Ampere's law, if this is going to be true for all coordinate systems, then C has got to be C for all coordinate systems. So that was his second postulate. So this was postulate 1. Postulate 2. Postulate 2 is the speed of light. The speed of light. I'm going to say more than invariance, an absolute. It's the speed of light. Well, how about if I just say the speed of light is C in all frames. Remember, when I say the speed of light, I mean in a vacuum. Is C in all frames. All frames. Okay, well, first of all, that explains Michelson-Morley experiment. He couldn't he couldn't measure the speed, anything but the speed of c. He didn't see any shifts right there. So this was his two postulates right here. So now we've got to, and you might say, why did he pick this one right here? Where did he see the problems? Well, he really saw it in time right here. How do you say that two things are simultaneous? Remember, he was a patent clerk. One of the things he had to look at there was, how do you synchronize train clocks, right? And they're moving with respect to each other. And but he thought about it much deeper than most other people thought about it. So how do you synchronize two clocks? Well, now we have a way, because now we say the speed of light is c in all frames. That is, it's independent of the speed of the light bulb. A light bulb could be moving at 90% the speed of light. It still only puts out light at the speed c right here. So let's say that we have a long stick right here. And let's say that the distance, that I'm right here in the middle, and over here I have two bulbs, light bulbs, that flash right here. And if I'm right in the middle, and these two flashes come to me, if those two events get to me at the same time, then they must be simultaneous, because they each took the same amount of time to get to me right here, because they're the same distance and everything goes at the same speed. So this is one way I can define how two objects are simultaneous to each other. I'm going to use light right here, because that's the only grip I have on the speed. So again, let's just, to make it simpler, let's just say that this thing is 2 light seconds. That is, it takes 2 seconds for light to go from one to the other. And you're right there. That means it took 1 second to get to you this way and 1 second to get to you that way. And if you got them both at the same time, then these two events must have occurred at the exact same time. So they're simultaneous to each other. Okay. Now, what happens, let's say this is, Frank right there. This is a stick that Frank has. And now we look at Mary. Remember, Mary's in red, so let me get a red one right here. At t equals 0, Mary and Frank are right next to each other. But as Mary is moving in this direction right here, and at t equals 0, the two light flashes occur. By the time Mary's going to be out here by the time this light gets to him, and this one over here is going to take longer. So Mary's going to say they're not simultaneous right here, even though when they both flashed they were the same distance. They're not the same, because now I'm here by the time it got to me, so she'd say this one occurred before that one. So she'd say they're not simultaneous. So Frank and Mary, t does not equal t prime, the time that Mary and Frank do not agree. So now let's go back to our old plots that look like this for a minute. Remember, we had an x versus t for Frank. So we had x versus t. And now this plot, remember, over here, the red and the black were right on top of each other because they shared time. Now they're not going to share time, so they're not going to be on top of each other right here. So we need to figure out what they are going to look like. I'm going to do one other thing. Since c is a constant, I'm going to make that c times t for two reasons. Number one, multiplying it by a constant just scales this. But at least now this has units of distance, this has units of distance, and at least we're comparing like things right here. So again, Frank would just be going straight up, so Frank would just be going straight up, and France is just going straight up, and Fred is going straight up, just like we had before. And now what's Mary doing? Well, Mary is just still going out like this, right here. There's still Mary, so this would be the CT prime right here. And now, what's the slope of this line? Before, the slope of this one over here was 1 over v. But let's just look at this. Suppose we take a point right there. This distance was VT, and this distance is CT. So the slope on this curve, which is the rise, CT, all over the run, which is VT, which is just C over V. So the slope now, the slope is C over V right there. Now, what happens if you shine light out there? If you shine light, if light is going, if Mary was moving at the speed of light, or just light traveling at the speed of light, this thing would be going out, you get C over C, which is 1. So on this curve, light is always at 45 degrees. So here, light is always at 45 degrees right there. The slope is 1 right here for light, right here. So when we had, let's say we have our long stick, I'm going to bring it right, redraw it down here. And here's our CT. And let's say we have a long stick right here. And here is Fred right there. He's right in the middle of the stick. And then at this time, the flashes occur. We know that the flash goes off at 45 degrees. And over here, it goes off 45 both ways, right? This one goes off but the light's coming this way at 45, and his motion is up here. And so we notice that they all met up, and he'd say, oh, that's a simultaneous event. This one right here got to me at the same time this one did, right here. But what happens to, not Mary? Mary would be off here like this, but what about Mo? Mo is right here. Let's say he was right there at this instant. He was just right there when these two flashes occurred. Remember, Mo goes off at an angle like this, right here. And so now you'll notice that this green signal got to him right here. Actually, I should do this in another color. This blue signal, this one right here, reaches him way out there. This one reaches him right there. And he'd say, oh no, that wasn't simultaneous right there. So this point and this point is not simultaneous to Matt, it's simultaneous to Fred right there. So we have to figure out what 2 points are actually the same time for Matt right here, So what are we going to do? Well, let's even, I think I'm going to, well, maybe we'll just draw a new one right here. So what I'm going to do is, first of all, let me come back to this case right here, where the flash occurred right there, and let me look at it from Mary's point of view. Remember, that was Matt, sorry, not from Mary, forget Mary, get her out of here. This is Fred right here. This was Fred, he's fixed. He's the one that went up like this. Frank is over here, Frank. Now, would Frank say that this is simultaneous right here? You might think no, because he'd see this one right away, and this would take a little bit longer to get to him. But he knows that this one is 2 light seconds away, let's say, and this one is 0 light seconds away. He'd say, oh, there was a 2-second difference, but I know that you're that distance apart. So I know that this is a simultaneous event right here, because I know how far away those 2 points are right here, and I know how long it takes light to get to me. So Frank would say it's a synchronous event right here. Fred would say it. Francis would say it, because they know where they are, and they can compensate for their position on this coordinate system. So everyone in Frank's coordinate system, all those people all measure the same time. So they're all going to measure, this is Everyone in Frank's coordinate system measures exactly the same time. They've all set their clocks relative to where they're at right here. Now, why don't we give this stick right here to Matt? If Matt has the stick, remember, it's going to be impossible to detect absolute motion. So if he's holding the stick and the two flashes occur, this should be simultaneous to Matt right here. Whoever's holding the stick is going to be simultaneous to them. So let's look at it. Here's our stick right here. So here's our stick right there. I'm going to make this stick 2L long right here. So this is L because Matt's right in the middle holding the stick. And here's another L right there. Okay, and we know we can draw that this end of the stick is going off like this with this slope of, remember we said the slope is C over V, slope equals C over V. And he's going off at that same slope, and this is going off like that. There's the 3 right there. This point right here would be what? L0. L0, and this point right here would be 2L0 right here. Okay, so now what's he going to do? Now we're going to have some light coming off this end. We know the light is going to go at 45 degrees, so it's going to come off like this to him. Okay, now first of all, we know the slope of these 3 lines. They're all C over V. And so if we wanted to get the equation of these lines right here, we can just use our equation of a line right here, which is y equals what? Mx plus b? For this curve right here, if we just wanted to get the equation of that curve, we know y equals mx plus b. Well, we know the slope, so the y value, remember y is ct, so we got ct equals the slope, which is C over V. X is x, this is my x-axis, plus my y-intercept, which is 0. Okay, we can cancel out the 2 c's, and you can just solve for x. X is equal to vt. Vt, I'm solving for x rather than y, but x is equal to vt. So that's the equation of this line. X is equal to vt. What's the equation of this line? Well, it's just shifted down by L, so it's just L plus xvt. So this x is equal to just vt plus L. Vt plus L. It's just shifted by L, and this one shifted by 2L. So this is just x equals vt plus 2L. Right there. So we got the equation of those 3 lines. Also, we know the equation of this line right here because we know the speed. This one is x equals vt. This one, you're just going at the speed of light. So this is x equals ct. X equals ct. So, let me draw that in a little bit better. X equals ct. Okay, so now if I wanted to find that point, the x value, I'll just call that point x1, and we'll call the y ct1. So the y is ct1. I want to find that. Well, I can find that because we can just equate these 2 lines right here, and that'll give it to me. So let's equate these 2. If we equate these 2, we got ct1 equals vt1 plus L. Okay, and we can solve for t1 right here. So let's bring this over to this side. So we got t1 times c minus v equals L, or t1 is equal to L all over c minus v. Or I could have said the y value, which is ct1, would just be put the c in there, but I'll just leave it like that. So there's the time at t1 right there. We can also get the x value because we can plug it into this equation right here. Sorry, not that equation. We'll plug it into either one of these two. We'll plug it into this one. Looks easier. x1 is just ct1. So x1 is just c times that. So it's just cl all over c minus v. So we've got that point, the time it took, well, we got that point where the light hit him right there. Now, if we come over to the other side, this going off at 45 degrees is not going to hit him right here. Why? Because this is not simultaneous with this. So what point is going to be simultaneous? Well, I know that light's got to be coming at me at 45 degrees. So why don't I start here and work backwards, go down at 45 degrees, right there. So that point and that point better be simultaneous because they both got to me. How do we find that point? Well, we know the slope of this. The slope of this is just -1. It's just light right here, and so the slope of that is -1. We have a point, we have a slope, so I can get the equation of that line right there. So if we plug in right there, what do we get? We get y equals mx. Well, I don't want to use that equation because I don't know the y-intercept. I'll say y minus y1 equals mx minus x1. We'll use that equation. And we'll use this point and that slope. So we get y, which is ct, minus the y value there, which is ct1, which is c times this, cl, all over c minus v, equals the slope, which is -1, times x minus this x1. And we already said x1 is right here. It's cl over c minus v. cl all over c minus v. Okay, so now that, let me solve for x out of that, and that'll give me the equation of this line right here. So how do we want to solve for this? Let me change the sign of everything here. So this becomes minus ct plus cl all over c minus v equals, and then this would just be plus now, x minus cl all over c minus v. And then let's bring this term over to the other side. But this term is exactly equal to that term, so there's going to be two of them. So we end up with x is equal to 2cl all over c minus v minus ct. So that right there is the equation of this line right there. So now we have the equation of that line. We also have the equation of this line, so we can find that point, which I'm going to call x2 ct2 right there. And we can find that point because I can set these two. I have the equation of this and I have the equation of that one. So let's set these two equations equal and we'll put in the 2 for the t right here. So we've got this equation, which is 2cl over c minus v minus ct2, and that should equal this equation, vt2 plus 2l. vt2 plus 2l, right there. Okay, and we just want to solve for t2. Okay, so we'll take this term, bring it over to this side, and we'll take the ct2 and put it on that side. So we've got 2cl all over c minus v. We're going to subtract this term over, so it's minus 2l. And that equals, if we take that term over to that side, we're adding them, so it's c plus v times t2. Maybe I'll get a common denominator between these two right here. So this is 2cl all over c minus v minus 2l c minus v all over c minus v equals C plus V times T2. And then right here I have a 2CL and I have a minus 2CL. They cancel out. And then I get a plus 2LV. So this whole thing here is just 2LV all over C minus V. And then I'll divide that out. So C minus V times C plus V is what? C squared minus V squared. So there's your T2. T2 is, there's my T2, and the Y value would really be C times that. And then to get X2, I can plug it into either this equation or this equation, my T2. I guess I'll plug it into this one right here. X2 is equal to V times this. So it's 2L V squared all over C squared minus V squared plus 2L. Plus 2L. And I think I will get a common denominator right here. C squared minus V squared, C squared minus V squared. Okay, so we notice in the top we get a 2LV squared, and we also get a minus 2LV squared. They're gone. So the only one that's left is a 2LC squared. So X2 is equal to 2LC squared all over C squared minus V squared. So that is my X2 for that point, and my Y, the Y value is really CT2, so we'll multiply both sides by C. So there's the Y value right there at this point. That point and that point should be simultaneous to Matt right here. This was Matt going up right there. Now, I should say, what is the slope of this line right here? Well, we know the rise and the run right here. The slope of that line is just the slope of that line right there is the rise, which is just CT2, which is just this, 2CLV, all over C squared minus V squared. There's the rise, all over the run, which is this, 2LC squared, all over C squared minus V squared. Now the C squared minus V squares drop out, the 2's drop out, one of the L's drops out, one of the C's drops out, and you're just left with V over C right here. So if you look back here, remember the slope of this is C over V. The slope of this is V over C. Slope equals V over C, which means that this angle and that angle are exactly the same right here. So we didn't have it right before. We had that they were both horizontal right here on the Galilean transformations, but that's not correct. What happens is both axes shift up kind of symmetrical. That is, space and time have pretty much, they're kind of symmetrical right here. And so your coordinate system in Mary's frame it's like this. Here's the equal x values right here. But equal time values are like this right here. So this would be the coordinate system from Mary's frame, the green one. Frank's would just be straight up and back right here. And so going through, we haven't come out with the transformation equations yet, but we need an equation that would pick a certain point here in the green coordinate system and shift it to the black coordinate system, remember. It's just like this. And that will be called our Lorentz transformations, and that will replace the Galilean transformations. It's going to be shifted up like that. So these are all equal times in Mary's frame right here. So what we want to do is, if we come over to here, okay, so now we have what's called the street lamp problem. Suppose here we have Frank and we have Mary going by right here. We have 5 street lamps, A, B, C, D, and E. And Frank sees, here's the location, A, B, C, D, and E. And here's my diagram. Remember, they're just going straight up right here. And they're turning on at different times. Street light A turns on here, B turns on up here, C, D, and E. Now first of all, they say, what is the order that they turn on in this diagram right here? Well, remember, in Frank's frame, equal times are horizontal lines. So we can see right here that both A and C turned on first, then E turned on, then D turned on, and then B turned on right here. And then they said, at what order did Frank see the light turn on? Well, Frank is only going to see it when the light gets to his eye. So when A flashed, remember the light goes at 45 degrees and he's going to see it up here. So he's going to say A came to him first, because remember Frank is up there. Then he's going to say C hit him. Then he's going to say D and B hit him right up there. And then E hit him right up there, because that's when the light actually hit his eye right there. Now they're saying Mary is going back down the road, and this is her, remember, her coordinate system gets bent in. If Mary's going the other way, it would bend out, but she's going this way, it bends in right here. And so this is equal times for Mary, and so all of these are equal times for Mary. So she's going to say, looks like E and C happened at the same time. These are equal times. She's also right there going to say that A and D occurred at equal times, and then B occurred even later right here. So these are the equal times right there. Then they say, what order did they reach her eyes? Her eyes right here. Well, A reached her eye. Remember, this is Mary going along this way. So A reached her eye right there. C reached her eye right there. D reached her eye right there. And E and B. So you'd say D and B hit her eye at the same time right there. And the last one is, where was the car, or where was Mary, when the street lamp D reaches it? Well, when D reaches her, where is she? Well, she's right in between lamp A and B, because she's right there when lamp D hit her. So we'll go through a lot of these type of diagrams. You notice you can figure it all out without any equations right here. We just have to know that these are equal times, and these are equal positions. So this diagram you just looked at, these diagrams right here, these XCT diagrams, they actually give them a name. They're called Minkowski diagrams. They make solving problems a lot easier right here. And we'll see later that there's a transformation between, the XCT and the X prime CT prime right for that point, and that's what we'll call the Lorentz transformations. And if we were to draw this for Mary, Mary says this, then Frank would be off like this. But we're always going to draw this from Frank's perspective. And so Mary's is always the same angles both guys right here. You notice that's a lot different than that homework I gave you on the very first assignment, the last problem. There I gave you a transformation where everything shifted like this. Here, everything is shifted like this. Everything shifting like this is a trigonometric rotation. We'll see later that this is a hyperbolic rotation right here. So it's a little bit different, a little strange right here. And so we're going to start getting some strange results about time and space right here. But we'll always come back and look at this diagram because it's a nice way. And the next time we'll derive the Lorentz transformations.